So today I am going to talk about a very interesting method or the formula, that is Newton-Cotes quadrature formula. And this formula is used to derive very important results like trapezoidal rule to do integration, Simpson's 1/3 rule and Simpson's 3/8 rule. So let us start with the Newton-Cotes quadrature formula. So for this, consider an integral and the integral is written like this, that integral I is from integral of f of x with respect to x from a to b. Suppose we are interested to determine this integral, and the situation is like this. And we are interested to find out the integral. Say this is the function and this is x-axis, and suppose this point is a and say this point is b. Suppose we are interested to find out the integral from a to b, and let us call a as x naught and let us call it as x naught plus nh, means it is xn. Means we have subdivided this region into n interval, means it is x1, it is x2, it is x3 and so on. It is xn minus 2, it is xn minus 1 and so on, it is xn, right? That's what we want to do. So here a is, we have assumed that it is equal to x naught and b is equal to xn, and let us call it as x naught plus nh because we have subdivided it into n intervals, each of width h, that is h is basically xi plus 1 minus xi. This is the width of the each interval which we have taken. So this means that AB interval divided into n equal subintervals each of equal width h, right? That's what I have chosen. So that means corresponding to every point we are having different value function. So the values of x are written here, which we have taken, and corresponding to it we have the different values of the function. So x is basically, it is x naught, x1, x2, let me take, yeah, it is x1, it is x2 and so on, xn minus 1 and xn. And corresponding to it, the value of the function will be f of naught, f of 1, f of 2 and f of n minus 1 and f of n. We have written it in this manner because I want to incorporate interpolation formula here, right? I will use interpolation formula, or I want to evaluate the function, right, using interpolation formula. So now to approximate function, fx, we will use Newton's Gregory formula. So that is the forward difference formula. So f of x can be approximated as f of naught plus s delta f naught plus s into s minus 1 over 2 factorial del square f naught, sorry, delta square plus s into s minus 1 s minus 2 over 3 factorial delta q f naught and so on. That's what we have to use here. And the value of S will be evaluated as, where S is equal to x minus x naught over h, right? And this delta f naught is equal to f1 minus f naught, and delta square f of naught is equal to delta f1 minus delta f naught, and delta f1 can be approximated as f2 minus f1, and its value will be here. It is minus f1 minus f naught. So it is f2 minus f1 plus f of naught. So that means it can be written as f2 minus 2f1 plus f of naught. So this is the value of this delta square f naught. That's what we have to keep in mind. This is one thing which we have to keep in mind. This is the second thing which we have to keep in mind. And third is what? Third is this delta cube f naught. So it is delta square f of 1 minus delta square of f of naught. It can be written as delta f1 f2 minus delta f1, and its value will be minus delta f naught. It is delta f naught and delta f1 minus delta f naught, which we have to keep in mind. So it is delta f2 minus delta f1 minus delta f1 plus delta f naught. So it can be written as delta f2 minus 2 delta f1 plus delta f naught. So let me put their values. So if I put their values, then it can be written as so delta f2 is what? F of 3 minus f of 1. Sorry, f of 3 minus f of 2, and minus 2 delta f1 is f2 minus f1, right? And then it is plus it will be f of 1 minus f of naught. Let me simplify it. F of 3, and it is minus f of 2 minus 2f of 2 plus 2f of 1, and here it is f of 1 minus f of naught. So this will become 3, this will become 3. So it can be written as f of 3 minus 3f2 plus 3f1 plus f of naught. So these are the three things which we have to keep in mind, right? This is simple elaboration of this and nothing else. So now I will use these values while deriving trapezoidal rule and Simpson's rule and Simpson's 1/3 and the Simpson 3/8 rule. This is for that. So we have to remember this for that, and I will talk about it in the later on lecture. So therefore this integral can be written as, this I can be written as, this I is equal to, its integral from a to b f of x dx, and it can also be written as x naught plus nh f of naught plus s del f naught delta f naught plus s into s minus 1 by 2 factorial delta square f naught, and 2 factorial can be simply written as 2 plus s into s minus 1 and s minus 2 over 6 del cube f naught plus and so on. We have left it here, and let us change the limits. So to change the limits, as we know that s is equal to x minus x naught by h, which implies that x is equal to x naught plus sh, and if I take differential, then dx can be written as dsh, right? So if I put these values here, and also as x approaches from x naught to x naught plus nh, similarly s approaches from 0 to n, because we want to change the limit. This is the step we are doing to change the limit. So if I put these values here, then how this will be written as, and here it is dx, right? I missed it. So if I use these values here, then integral can be written as, that's integral from 0 to n, it is f naught plus s delta f naught plus s into s minus 1, or s square minus s, let me simplify it, it is x square minus s square minus s by 2, and it is delta square f of naught plus s cube minus 2s square, sorry, minus 3s square plus 2s divided by 6, and del q f of naught, and outside it is plus, and so on, it is h ds, and h can be taken outside. So if I take it outside, the integral, so it is h, and let us take every integral separately. So if I take its integral, so it is f naught ds, its integral, this part. Now let us take its integral. So here it can be written as plus s del f naught, sorry, delta f naught, its integral, plus s square minus s by 2 delta square f of naught ds, its integral, plus s cube minus 3s square plus 2s divided by 6, and delta cube f of naught ds, and so on, and it is a limit from 0 to n. That's what we will take, right? So now let us take their integrals. So if I take their integrals, then it will become, let us take their integral. So if I take its integral, then its integral will be, f naught is a constant, and the integral of ds will be s, right? So its value means, taking their respective integrals, it can be written as h, it is f naught s minus, the integral of s will be s square by 2, delta f naught will remain as it is, plus s cube by 3 minus s square by 2, and this 1 by 2, it is outside, and it is their integral, right? It is delta square f of naught plus 1 by 6 s4 over 4 minus s cube, because this 3 will cancel out, and it is plus s square, that's what I am getting if I take its integral, and delta cube f naught, it can be taken here, and so on, and it's a integral from 0 to n, so I am putting limit here from 0 to n, and if I put this limit 0 to n, so it will be simply written as h, means substituting these limits n and 0 to n, so it is n minus n square by 2 del f naught plus 1 by 2 n cube by 3 minus n square by 2 delta square f naught 1 by 6 n4 over 4 minus n cube by 3, sorry, n cube and plus n square delta cube f naught plus and so on, right? So I have substituted the limits, and here I can take n common from every term because it is sitting with every term. So if it is sitting with every term, then I can write down that integral is equal to nh. Inside it is f naught plus n by 2 delta f naught plus 1 by 2 n square by 3 minus n by 2, and it is delta square f naught plus 1 by 6, it is n cube by 4 minus n square plus n, and it is delta cube f of naught plus and so on. So the integral which I am getting here, this is known as Newton-Cotes formula, and which is used to derive various other important formulae or rules like trapezoidal rule, Simpson's 1/3 rule, then Simpson's 3/8 rule, right? These are the three rules, or other rules can also be derived, but I will talk about only these three, which we will derive using this Newton-Cotes formula, quadrature formula, right? And they can be derived in a very simple. If you remember this formula, and if you put n is equal to 1 here, then we can derive trapezoidal rule, and if we will use n is equal to 2, then we can derive Simpson's rule, and similarly if we will put n is equal to 3, then Simpson's 3/8 rule can be derived from this Newton-Cotes formula, and if we will put n is equal to 4, then other rules can also be derived using this. So in the next lecture I will talk about that how trapezoidal rule can be derived using Newton-Cotes formula, and in the earlier lecture I talked about the derivation of trapezoidal rule by simple method, right? So that's all for this today's lecture.